In the previous lectures, we have seen the need for studying thermodynamics and the importance of thermodynamics. In this lecture, we'll now look at some basic concepts and definitions that we need for systematic analysis of engineering systems using thermodynamics. So let us discuss what we mean by system and its surroundings. System is defined as a certain portion of physical universe that is enclosed by real or imaginary boundaries, and that boundary separates the system from its surroundings. That is, the rest of the universe except the system is called its surrounding. To put it simply, the system is the matter that we want to study, and everything else except the system is called its surroundings. So the system has to be unambiguously demarcated by a boundary, and this boundary can be real or imaginary, that encloses the matter of interest. And the boundary that separates the system is termed as system boundary. While doing thermodynamic analysis, for clarity, the system boundary must be marked on a sketch of the system, and a common convention is that if you have a diagram of the system, then you demarcate this system boundary using a dashed line. Let's look at examples of few systems. So here, let's say we have this thermos flask in which we have water and its vapor. So if we want to perform thermodynamic analysis on this water that is inside this thermos flask, then choose system boundary that is shown yellow dashed line, and this line touches the wall of the thermos flask. Similarly, if you have, let's say, a system where you have a cylinder piston arrangement so that there's a gas inside the piston and you want to look at gas, then gas is your system and the system boundary is this dashed line, the yellow color. Similarly, if you want to perform thermodynamic analysis of a battery, let's say lead acid battery, which has these positive and negative terminals, then we can consider system boundary such as so whenever you do some thermodynamic, then the first step your thermodynamic analysis is to mark the system boundary so that you separate out the system that you want to analyze from its surroundings. So the examples that we have seen over here are those where there is no mass transfer across the system boundary. So in general, there can be mass transfer across the system boundary, and there can also be transfer of energy. So the definition of system and the system boundary in general is very general, and the system boundary allow mass can allow energy transfer. Later we'll see this energy can be in terms of heat, in terms of work, and these boundaries, system boundary, can be rigid. They may also be deformable. For example, in this thermos flask, we have a rigid boundary. But here, if we pull this piston up, then our boundary will be deformable. For a particular case, when no mass transfer takes place across the system boundary, we term that fixed amount of matter enclosed within the system boundary as control mass. So a control mass system is a particular type of system where there is no mass transfer across the system boundaries, but there can be transfer of energy across the system boundary. So the examples that you see over here piston cylinder, thermos flask, battery are all examples of a control mass system. Because there is no mass flow across the system boundaries, the control mass systems are also called as closed systems. On the other hand, if we have a system which also allows mass transfer across the system boundaries, such kind of systems are called control volume. And to mention specifically that there is mass transfer across the system boundary, such systems are also called as open systems. So the examples that we see over here are all examples of closed systems because there is no mass transfer the system boundaries that we have by this yellow dashed line. So let us look at examples of some control volume systems or open systems. And these are used interchangeably. In one of our previous lectures, we've seen the example of a steam turbine that is used in a steam power plant. So if we demarcate the system boundary as this, then clearly there is flow of steam into this system and flow of low pressure steam out of this system. So this is an example of open system. Such systems have to be analyzed by invoking a control volume. That is everything that is enclosed inside this system boundary. Another example that we are familiar with, and this is a household example, is the reverse osmosis water purifier. So here what we have is, if we consider system boundary known as this dotted line, then we have this feed water or the tap water that goes into this water purifier, and it splits up into two streams. One is the drinking water, which has less salt content, and another is brine, which has higher salt content. So you can see that there is mass transfer across the system boundaries. This is also an open system, and we have to analyze this using the control volume. Note that the control volume include both the substance or the matter that is closed in the system and also the devices. So here in both of these examples, we've seen that the system boundary not only contains the matter or the substance which we want to analyze, and also the various devices that make up this whole system. Now going back to the control mass system, so a particular type of a control mass or a closed system is called an isolated system. So isolated systems are those that do not interact with their surroundings. So that means there is no mass transfer and no energy transfer across the system boundaries, and that is an example of an isolated system. So clearly, if we look at this thermos flask, hot water and its vapor, and if we say that the walls are perfectly insulating, then this system would be an isolated system. And if you look at the example of this battery, then it might transfer heat to the surroundings. So even though there's no mass transfer across the system boundaries, but there is transfer of energy, and that's why this is not isolated. So another definition that you need is walls. So walls are the system boundary, and walls are those system boundaries that do not allow mass transfer to take place across themselves. So as is obvious, so we have this is, let's say, a wall. Now walls can be rigid or deformable, and also the wall can be of two types. One is adiabatic. So strictly speaking, if we want to consider thermos flask as an isolated system, then walls need to be adiabatic. Adiabatic walls are those which do not allow transfer of heat across them, whereas later on, in some examples, we'll call the walls as diathermal walls. Diathermal walls are the opposite of adiabatic walls. So diathermal walls are those which allow heat transfer across them. For example, the walls of this battery can be said to be diathermal because they allow transfer of heat from the system to the surrounding. So for a given engineering system, whether the system that you are considering is an open system or a closed system, or a control mass system or a control volume system, depends upon the choice of the system boundary that you choose. So I'll leave this as an exercise for you. If you wish, you can answer the comment section. So consider that if you have system boundary that I'm showing red color over here, then can you say that this system is open or closed? Similarly, let's consider another problem. So here we have a throttling valve. If you remember from the first lecture where we discussed this vapor compression refrigerator. So in this vapor compression refrigerator, if you look at this throttling valve and you consider the system boundary around this throttling valve, then again, can you say whether the throttling valve, or can you say that this system here is open or closed? And to find the answer, all you have to see whether there is mass transfer taking place across the system boundary. That's how we classify open or closed system. Now let's look at some more definitions. Later on, we are going to use these terms again and again. Another definition, that of a working substance. So the matter or the material that is inside the system and also that is flowing in out of the system is called the working substance. For example, you have, let's say, the throttling valve that we've looked at in the previous exercise. Then in the throttling valve, the working substance is the refrigerant. Similarly, in a steam power plant, the working substance is water. Now, the working substance might be composed of different components. So this is another definition. So components refer to substances with different chemical composition. For example, if you recall our lecture on the rocket engine, there we had seen that the liquid propellant rocket, you inject the fuel and the oxidizer, for example, with hydrogen, oxygen, and here these two gases react. So the mixture of hydrogen, oxygen is composed of two components, that is hydrogen and oxygen gas. Similarly, that air is a mixture of different components such as nitrogen, oxygen, carbon dioxide, other gases. So a phase is another thing that you need to know. So phase is referred to as a quantity of matter that is homogeneous. For example, let's go back to this thermos flask. Let's for the moment assume that this thermos flask is evacuated, so only thing that you have inside is this water, liquid phase, and vapor phase. Then we say that water is present in two phases, liquid and vapor phase. These phases are separated by a charge boundary called as the phase boundary. Similarly, if you have ice and water mixed, then you will have water in solid and liquid phase. So in most part of this course, we are going to consider what we call as a pure substance. And this term will come again and again in the course. So a pure substance is one that has only one component. For example, water is a pure substance, even though it can be in different phases, but it still has the same composition in both the phases. So the composition of water, that means water H2O, does not change chemical nature in the vapor phase, liquid phase, and that's why we treat it as a pure substance which has only one component. Similarly, pure carbon dioxide can also be treated as a pure substance. Next, we look at the definitions of properties, in particular, extensive properties. So thermodynamic properties can be classified into extensive properties. So we've seen that how we define a system. Now every system has some characteristics by which we can describe its physical conditions, and these characteristics, for example, pressure, volume, density, temperature, are called the properties. Quickly speaking, what we mean is properties of the working substance that is contained the system. So these all properties are macroscopic in nature. That means when we measure these properties, as we have seen in previous lectures, these properties are measured due to presence of large number of particles. Therefore, these are macroscopic in nature. So now these properties can be classified into intensive and extensive properties. So extensive properties are those that depend upon the mass or the size of the system. So clearly, examples of extensive properties are mass and volume. On the other hand, intensive properties are those that do not depend upon the mass of the substance that is contained in the system. And the examples of intensive properties are pressure and density. Now, extensive properties, so if you have any extensive property, you can also convert it into intensive property. For example, you have volume, you consider volume per unit mass, that is what we call as specific volume. So specific volume is an intensive quantity. So all extensive properties can be converted to intensive properties by taking those properties per unit mass. Based on these properties of the substance, we are going to define the state of the system. And in particular, we are going to look at the equilibrium state of the system.